Hello again, Physics 20s. Going to talk today about Newton's third and final law of motion. Very, very nice. Sometimes on multiple choice tests and stuff, you see Newton's fourth law. Nope, we didn't go that far. It is Newton's third law of motion. And this is another one of those ones where we kind of have the idea of like what's the need to know for the next level for Physics 30. So the need to know is the ideas behind this, and then some of the more simple math, and I'll show you exactly what that is. Well, we'll talk about what that is. It kind of fits in with the ideas anyways. Any of the box problems, and it'll make a lot more sense when we start talking about them here. Any of the problems with boxes that's more specific to Physics 20. It is very important for Physics 20, but it's not really super important for the next level. So that is sort of the enrichment for this this learning from home that we're doing, that we're dealing with here. So anyways, yeah, let's jump right in and let's have a look. So the very first thing that we want to talk about with Newton's third law is, well, if I've got this tennis ball, and the tennis ball has a weight of 1 Newton, we actually got to go back to the very first lesson. Weight of 1 Newton. Does anybody remember what weight means in physics? It's our force of gravity, right? So weight is force of gravity. If I say I have a 1 Newton tennis ball, that means its force of gravity is 1 Newton, and its weight is 1 Newton. If I say I'm an 800 Newton person, so Mr. Dukley is about 800 Newtons, that's my weight, that's also my force of gravity. Cool. So I got this tennis ball, it's got a force of gravity of 1 Newton going downwards. If it's being lifted at a constant speed, what does the applied force need to be? So the idea of constant speed, that tells us F net is equal to 0. The applied force needs to be equal but opposite. So my applied force by my hand must be 1 Newton upwards. So this is the big idea of Newton's third law. Anytime we have a force, there's always got to be some sort of balancing force, some sort of equal but opposite thing. So just kind of one thing to note in this, and we'll talk about this as we go through a little bit more, the force of gravity is pushing the ball down on my hand. So it's a force that's acting on the ball, pushing it down on my hand. The applied force is pushing it upwards. It's always going to be an opposite things. So Newton's third law, if we wanted to put this into sort of a definition-y type thing, for every action force, there is an equal but opposite reaction force. So when we check out this skateboarder, she is pushing on the wall. So she is applying a force to the wall, and notice it is on the wall, but the wall is also applying a force on the person. So we always have those two different forces, and they're always acting on opposite objects. So sort of breaking it up, here's the force and the free body diagram for the wall, or the force diagram for the wall. So we've got the person pushing on the wall, and the force diagram for the other object, not that people are really objects, but in this case for the other person, is, again, it's the free body diagram. It is the person being pushed from the wall. So they are equal but opposite, and they are on different things, right? So consider this one, right? And this is, again, sort of big ideas. So you kick a soccer ball. You might put 150 newtons of force onto that soccer ball. That's cool. What's my action force? Action force is the 150 newtons that is on the soccer ball. So 150 newtons on the ball. What's my reaction force then? My reaction force is we have 150 newtons acting on the foot. So I'm even going to get rid of the ball here. I'm going to draw a foot. Oh boy, better put some, okay. This is getting, that's a foot. The free body diagram or force diagram in the foot has to have that 150 newtons just acting on the foot. So they are an opposite objects as well. So different objects, the action and reaction force is what I'm getting at with this. So something that's very, very important to note. So just think about this one for a second. You put your video on pause if you want to for this. How does a rocket accelerate upwards? Just think about that for a second. So obviously the force of gravity is pulling the rocket downwards. What does the rocket have to shoot out of its tail, I guess? I don't know what you'd call the bottom part of a rocket down here. What is it shooting out? it's shooting out a ton of gas particles, in particular mostly water, because I think they use hydrogen for the most part for rockets. So it burns with the oxygen and then produces water. So there's a very large force acting on all of those individual particles. So you're going to have a force pushing those particles downwards. We know from Newton's third law that we need an equal but opposite force pushing the rocket upwards. So in each individual particle, no, there's not much force. But when you add up all of those particles being forced downwards out the bottom of the rocket, that becomes very, very, very significant. Cool. So here's a bit of an issue, a bit of a conundrum for you. You push on a wall, you're standing on a skateboard again, just like that girl was in the first one. There's a pretty crummy skateboard, but you're standing on a skateboard, you push on a wall, you accelerate backwards. So you are like, yeah, cool, dude. That's how I picture skateboarders talking. But anyways, you accelerate one way. Does the wall, acceleration for the wall, accelerate? Right? And we kind of already mentioned this before in our very, very last lesson. So if we know that the force of 1 on 2 is equal to the force of 2 on 1. So opposite direction. So we'll put a negative in there to represent that. So let's say that force 1 and 2, this is me or the skateboarder. Skateboard. I should have wrote me. It's way smaller. Skateboard. Cool. So the skateboarder has a relatively small mass and going to have a relatively large acceleration. The wall, on the other hand, like what are we talking about when we're talking about the wall? The wall is attached to the ground is the earth. We are going to have a very, very, very extremely big mass, just a ridiculously large mass, and we're going to have a ridiculously small acceleration. That's when you blow this up, it's supposed to say acceleration, but it's just so small that you can't even see it in that case, right? And that's sort of the idea is, yeah, the Earth is going to accelerate, but it's going to be so dang small, you're never going to be able to measure that. And also there's a billion other things going on in the Earth, bigger forces than, you know, some cool person pushing a skateboard off their wall. Yeah, I'm doing a terrible job with that. But anyways, hopefully that makes sense for people. So that's sort of a bit of space there. And our first example, this is something that you'll want to definitely know about. So you have an 80-kilogram boy exerts a 500 Newton force to the right on a 60-kilogram girl. At the same time, the girl exerts a 700 Newton force to the left on the boy. So let's just go through. We've got an 80-kilogram boy, so that's the mass of the boy, let's say MB, exerts a 500 Newton force to the right on a 60 gram, so we'll call that mass of the girl. So M, use capital G because that looks too much like gravity for me. So M times or mg, capital G. At the same time, the girl exerts 700 newtons to the left on the boy. Perfect. So let's set this up a little bit here. What do I got? Yeah, I've got these two. I've got those two. And then I've got the answer. So let's go back. You know what I'm going to do? Just going to draw this all by myself here. Add an extra page. Ooh, that might not work. Scroll down a little bit. Yeah, whatever. We'll draw it over here. So I have to make sure I'm neat and organized. So essentially what I've got is here is the boy. You can tell it's a boy because it's got a B in his face. And here is the girl. You never guess how you're going to be able to tell it's a girl. G in her face. So there's the boy and the girl. So the boy is pushing to the right with a 500 Newton force on the girl. Cool. But what's Newton's third law say? So if the boy pushes on the girl with 500 newtons, what happens to the boy? Well, the boy gets an equal to opposite force of 500 newtons. Cool. So not so bad. Nice. Then it says the girl exerts a 700 Newton force to the left on the boy. So the boy, this girl really doesn't like that guy for some reason, but exerts a 700 Newton force on the boy. So that's the girl pushing on the boy. Cool. But then again, what does Newton's third law say? Newton's third law says equal to opposite forces. So if the girl's applying a force on the boy, whether he knows it or likes it or not, is also applying a force of 700 newtons on the girl. Cool. So once we've got our free body diagram set up for this, once we understand that, yeah, the boy is pushing the girl with a force of 500 newtons, but because of Newton's second law, the girl's pushing right back with 500 newtons, and vice versa with our 700 newtons on the bottom there. Once we understand that, it's not so bad. So it says, determine the acceleration of each person. So if I'm looking at the boy, well, I just say the net force acting on the boy, well, it's 500 plus 700 newtons, so 500 plus 700 newtons. Those are both towards the left. So let's see, that's going to be 1,100 newtons left. Perfect, we can look at that. And actually, we might as well look at the girl now as well. So the net force, F net on the girl, is going to be equal to 500 newtons plus 700 newtons. But in this case, towards the right, so that's 1,100 newtons towards the right. And if those are the only two forces that are acting on them, well then, like the pushing forces, then yeah, it makes sense that they're still equal but opposite. So the very, very, very last step for this one is it's asking us to figure out the acceleration. So this is where it gets a little bit different. So the net force on the boy is going to be equal to the mass of the boy times the acceleration. So the acceleration must be equal to the net force divided by the mass, all of the boy. So that's 1,100 newtons towards the left, divided by how massive was this boy? 80 kilograms. 80 kilograms. So 1,100 divided by 80, I'd better just get my calculator out here. 1,100 divided by 80, and you can also have a look at this. I think that will be 15 meters per second squared towards the left. Cool, okay, so we found the acceleration for the boy. Could we do the same thing for the girl? Absolutely, right? So we just say F net for the girl is mass of girl times acceleration of the girl. So the acceleration of the girl is F net over mass. So that's 1,100 newtons, this time towards the right, divided by, what was she, 60 newtons or something like that? Or sorry, 60 kilograms, I think so. 60 kilograms, and I believe this one works out too, so let me just check in the old calculator here. You should be doing the same. 20 meters per second squared towards the right. Cool. So not too bad. Again, the big idea is, like the really big idea is if there's a force on one object, can I make it so it fits all? There's got to be the exact same force happening on the other object whenever two objects interfere with each other. That's actually huge. All of these three laws are actually pretty huge for Physics 30. So at this point, like what we're looking at right now, this is our essential. So up to here is our essential learning, and if you're looking for some practice, which please absolutely do some practice, questions 1, 2, 3, and 5 from lesson, what lesson is this one again? Lesson 4 is what you're looking at. After this, so questions 4 and 6, I believe, are the enrichment, which I just spelled wrong, enrichment, yeah, it's a little messy, but you get the idea. 4 plus 6 are the questions. And again, if you're done now, cool. You want to check out the essentials and go from there. If you're feeling like that's good for the time being, that's cool. If you want to look at a little bit of the enrichment stuff, just stick with us. So for the people who are leaving, bye for now. We'll talk to you again soon. For the people who are sticking with us, let's check it out. Okay, so good. You don't have this one in your booklet. This is just sort of the big idea. So if I have two crates lined up, two crates, crate A and crate B, and I am pushing on crate B. So here's maybe me pushing on crate B with a force of 80 newtons. I have to push all of B and all of A. So that 80 newtons is pushing the entire thing. But if I were to think about just what's pushing on A, so only what's pushing on A, it's realistically just box B that is pushing on A, and it's going to take less force to push A all by itself than it is to push B. I hope that makes sense for people. If it doesn't, try it out in your house. Line up a couple things. Line up the ketchup, barbecue sauce, mustard, something like that. Try pushing all three of them lined up. It's going to take a lot more force than it is pushing one of those three things. You can try that out. Actually, barbecue mustard, stuff like that might not work so well. Try bigger things like your table and chairs or something. I don't know. Cool. So what these questions actually look for is the force of A on B and the force of B on A. So it's the force between the two carts or the two blocks. So if we wanted to solve for this, our first step is find the acceleration of the crates of the, and I'm going to write this out, the whole thing, the whole entire thing. So if I wanted to look at the whole entire thing, I would look at, and I'd say it's always going to come back to these. We've said that before. F net is mass times acceleration, and F net is the sum of all the forces. So in this case, it's just that force F. So what that means is, if I know that the net force is just force F, I know it's just 80 newtons, right? I can go ahead and solve for my acceleration. So my acceleration is F net divided by the mass. I'm going to be very specific, and I might actually solve this here. 80 newtons divided by my mass. It is my total mass of 16 kilograms. So total mass. Nice. So 80 over 16, I forget where I put my calculator, so you plug that one in. Do I have the answer up here? Ah, good, I do. 5 meters per second towards the left, and I know it's towards the left because the only force I had was 80 towards the left. So we figure out our acceleration, and that's the acceleration of the entire system. The whole thing, if they're attached, is accelerating at 80. Now, if I wanted to go through and look at between the boxes, now the next step is to look at one box. Look at one box. And honestly, it doesn't matter which box you look at. You could look at A all by itself. So here's box A, and the only force acting on A is B on A. So if you know the acceleration and you know that force, you should be able to figure out, or sorry, and you know, let me collect my thoughts a little bit here. So if you know that the net force is mass times acceleration, just the mass of block A, and you just figured out the acceleration for the whole system, which is the same, you can figure out the net force, and you know that the net force is just the force of B on A. Awesome, that's not so bad. If we're looking at B, it's a little bit more challenging, but it's still not the end of the world. So if I'm looking at B, I've got that force F, which is 80 newtons. And I've got the force of A on B. So A pushing back on B. Nice. So I know for this one, my net force is mass times acceleration. So we solved for acceleration before. We're just using the mass of block B, so I can figure out my net force, and then my net force is going to be equal to that force F plus my force of A on B. So you can go ahead and solve for that force of A on B. Keep in mind the direction here is going to be kind of important. So I hope this makes sense. We'll look at the typed out answer a little bit better here. Or a little bit quicker, and it will work out to be the exact same thing. So if we're analyzing just block A, we say net force on block A is mass times acceleration. The only force that's acting on it is B on A. So we go through and we figure out the net force, which is force B on A, which is 30 newtons. 30 newtons towards the left is what we'd look at in this case. Cool, so if you need to put that on pause and check it out a little further, that's cool. If we look at the next one, same sort of idea. So the accelerated motion, it's still unbalanced force, it's still all those pieces. We are just looking at block B. So net force for block B is mass times acceleration. This one, they've kind of plugged it in a little bit more, so that's force F. And they've said, oh, it's kind of tricky here. Left is positive and right is negative, which is okay. It kind of means that this one's going to be positive and this one's plus a negative, which they just said minus a negative, or sorry, minus the positive. Oof, I'm losing it here. But same sort of idea. So we rearrange and it works out to be 30 newtons. Again, if you need to, put this on pause, study it for a few minutes and see what you get. So your actual example then, I'm going to get you to pause the video and and see if you can use those big ideas to figure out the force of B on A. So force of B on A. That being said, one big hint that I'll give you before you pause is the force of A on B, remember, is going to be the exact same thing. So before you put it in pause, remember, find the acceleration for the entire system. Once you have the entire acceleration for the entire system, analyze one of the blocks. Big hint, try and analyze A, and if you can figure out why you can't analyze B, good for you. So put it on pause. I'm going to do the same thing. I'm going to solve, and we'll catch up in a minute or two. All right, so depending on where you're at, I'm hoping that you got the acceleration. Again, this is for the whole system that we've got here. Maybe I'll do a different color and highlight a bit. For the whole system, everything that we see here. So I know that the net force is mass times acceleration, and I know that the net force is sum of all the forces. So my first step is I just solve for the net force. Sum of all the forces, just add up all of the forces, keeping in mind direction. So I'm calling right positive and therefore left is negative. Turns out that my net force acting on the whole entire thing as one gigantic object, even though it's made of 3 smaller objects, is 250 newtons towards the right, or positive 250 newtons. Then I go through and I rearrange. So acceleration is net force divided by mass. Because I'm talking about the whole system, I use the entire net force for the whole system, and I use the entire mass of the whole system. So the total mass, and again works out to be 2.5 meters per second towards the right. Cool. So if this helps out with our next step, that's cool. You can just keep watching the video. I haven't solved it yet. I'm going to pause it and solve it. And if you haven't solved for that last bit, again, you do the same. Pause it and solve it. And the hint that I gave before was focus on block A. All right, cool. So like we said, we are going to analyze block A all by itself. So I made a free body diagram. That's over here, a free body diagram for block A. So I got block A being 20 kilograms. I know that the 2 forces that are acting on block A, I got force 1 is 400 newtons, and I've got force of B pushing back on A. And I also know that my acceleration is 2.5 meters per second squared. Nice. So then I can go through and I can start to think about this. And it always comes back to these two things. F net is the sum of all the forces, and F net is mass times acceleration. So I just said, well, it's the sum of all the forces. That's F1 plus force of B on A. So I'm solving for, and I'm looking for, rearranging to see force of B on A. So I rearrange, that's F net minus F1. F net, I realistically know is mass times acceleration. So I just substitute that in, plug in all the numbers, turns out to be 350 newtons, negative 350 newtons, which is 350 newtons towards the left. Now you might be thinking, well, that's the force of A on B, 350 newtons towards the left. That's not really what the question was asking, was it? So let's just go back to that one little tiny piece, and it is the whole idea of Newton's third law. So if B is pushing on A, and I think I wrote that out a little bit backwards up here, so let's just get rid of this, and I'll say that's force of B on A. If force of B on A is negative 350 newtons, or 350 newtons towards the left, well, we know Newton's third law says we've always got equal but opposite forces, so the force of A on B must be positive 350 newtons. So there is our actual answer for this. How hard is A pushing on B? It's pushing with a force of 350 newtons. Cool. So that is the extension piece again, or the enrichment piece, I think I was calling it. So questions 4 to 6, 4 plus 6, I should say, are my enrichment piece. So if you're looking to do all of it, it's pretty much every question in the booklet if you're doing the enrichment pieces. So anyways, thanks for hanging out if you stayed this far. And well, Physics 20s. Oh, I should warn you with this one as well. We're actually next going to do lesson 9, so explaining stuff with Newton's laws. So we're going to go a little bit out of order here. Excuse me, a little bit out of order here. But I'll explain that in the notes very, very clearly on our Google Classroom. So anyways, I will talk to everybody again soon. Bye for now.